and welcome to the Louisiana Department of Education's recorded webinar series presented by the Charles A. Dana Center at the University of Texas at Austin. This session of the series is about the Louisiana Instructional Model and Planning Guide. At the Dana Center, we focus on both K-12 and higher education systems. We bring an equity lens to our work in order to provide access to high-quality, relevant mathematics and science education. Our K-12 math and science work is research-based and has a sustained approach. We work across all aspects of K-12 education, from classroom, schools, and districts through states and national organizations. We work to ensure that teachers, administrators, and students have the essential tools they need to foster learning and engagement. For our K-12 to higher education transition, or our Launchers initiative, we focus on reimagining math education from critical junior year of high school into the first year of post-secondary, and engage leaders, experts, and advocates from K-12, higher education, and business and industry. And finally, for our higher education math work, or the Dana Center Mathematics Pathways, we support students in navigating from high school into and through entry-level math courses at 2- and 4-year institutions. Within our K-12 work, we have helped develop and implement math and science resources that are used in many classrooms. In this session, we will explore the Louisiana instructional model through looking at an open-side unit. Consider how the instructional model supports units to be phenomena-based, coherent for students, driven by evidence, collaborative, and equitable, and analyze how the planning guide for instruction can be used to unpack and plan for three-dimensional instruction. Listed are OpenSciED's key instructional elements. We will reflect using these key instructional elements as we explore the instructional model. You should have a handout that looks like the image on the right. Take a few minutes to read the descriptions of the 5 key elements. Whenever it is suggested that you take a few minutes to read or do something, you will likely want to hit the pause button. This is the full Louisiana instructional model. It includes 5 routines and a process of communicating scientific reasoning. We will explore the instructional model through looking at an OpenSciED unit called Sound Waves. We will walk through the lessons of the unit primarily with a teacher perspective. However, I will occasionally ask you to do a task as if you're a student. The first step in the instructional model is to experience a phenomenon using what is known as an anchoring phenomenon routine. These maroon slides are from the OpenSciED unit and are meant to be shown to students. The launch of a unit and of an anchoring phenomenon starts with a phenomenon that students can experience in some way. They can experience it in person, they can watch a video or see a picture. In this case, students are shown a video and asked to write down what they notice as they watch the video and what they have questions about, what they wonder. As we watch the video now, write down your noticings and wonderings.
I work with these guys.
You will notice that this slide is labeled A. We are about to skip to slide D. Students would have an opportunity to share what they noticed and what they wondered with each other. OpenSciED is built on the understanding that students learn through discourse with their peers, so there are many opportunities for them to share. Sometimes this sharing occurs in partners, sometimes in whole group. Sometimes sharing starts with partners to allow students to gain comfort with their idea before sharing with a larger group. Given the medium of a webinar, we will be skipping some of the slides that support student discourse. This is not meant to imply that we suggest skipping these opportunities, as they are critical for student learning. Through student discourse, the class comes to an idea that a speaker inside a truck is doing something to make the window move. At this point, the teacher can suggest that it might be helpful if the class could observe something like what's happening in the video, but up close, to actually see the speaker, which we couldn't see in the video. Students can be prompted to identify how this setup models what they saw in the video and how it can help them make further observations. Then students can notice and wonder what the speaker is doing when it's making sounds, and what is happening while the speaker is making sounds that might help us understand what's causing the pattern we see in the window. Now that students have made a variety of observations, it's a good time to shift from noticing to trying to explain what's causing the patterns that we observe. At this point, students will likely agree on what's happening in the video, but will have different ideas about how the speaker is making the window move. Students can use the handout called Making Sense to support them as they develop initial models. The handout encourages students to develop models that show what's happening at a zoomed-in scale at 3 places: the surface of the speaker, in the air between the speaker and the window, and at the surface of the window. The handout also directs students to use words to explain their models. Channeling your inner middle school student, take a minute to create an initial model that you believe a student might create. Taking time to create what you believe a student may create can help you better understand what is being asked of students and better prepared to support student ideas. At this point, students would work together to compare models with partners and then with the class, following the pattern previously mentioned of moving from individual thinking, partner or small group sharing and thinking, and finally full class sharing and thinking. As the full class shares, they create a consensus model that represents the ideas they agree on and what they still have questions about. This is a possible initial consensus model. You will notice that students have lots of questions. At this point, the teacher can transition by saying, "We agreed that we still have a lot of questions about how the speaker is making the window move. One strategy that we can use to help figure out how something works is to consider other times when we've seen something similar. Many times, figuring out how one thing works helps explain a bunch of other related phenomena." Take a moment to read through the questions on this slide and brainstorm some related phenomena. As students share, it may be helpful to highlight instruments as well as objects making sounds that aren't necessarily designed to make sound, like a floor when a person walks on it. Between students' initial wonderings, initial models, and all the related phenomena, there are a lot of potential questions that students could ask and investigate to help them figure out how sound from one object can make something else move. Again, channeling your inner middle school student, take a minute to brainstorm at least 2 questions. It's okay if these questions aren't fully formed or if you're not sure how to phrase them, as there'll be an opportunity to refine them. Now that students have brainstormed a lot of questions about the truck video, the speaker, and other similar phenomena, they're going to revise a couple of questions before contributing them to the driving question board. These sentence starters can help students reframe their questions into how or why, more causal and mechanistic questions. As they revise their questions, students are asked to write the questions in marker on sticky notes, 1 per note. Students bring their questions to a scientist circle. They sit together and collaborate to build their driving question board. Each student's question is shared, and the board is built with questions grouped together based on questions that are most related. Once the DQB is done, the teacher suggests that there might be a broader question that our model and DQB seek to answer. How can we detect sound from a distance? Now that students have created a lot of questions, they can start brainstorming what data they need to answer their questions and how they can obtain that data. Students start this process by individually capturing their ideas for investigations and data needed, and then the class will create a list together. Take a minute to read the questions on this slide that will be presented to students. To explain this phenomenon, students are going to need to investigate all three parts of the model, and they likely have questions and investigations about all three. The teacher is guided to say, since we're already investigating the sound source by making observations of the speaker, it seems like that Since we're already investigating the sound source by making observations of the speaker, it seems like that part of our model is a good place to start. We just walked through the anchoring phenomena routine for this unit. The anchoring phenomena routine consists of 4 elements: exploring the anchoring phenomena, attempting to make sense of the anchoring phenomena, identifying related phenomena, and developing questions and next steps. Think back to the routine for the sounds unit we just walked through. Can you identify each of these elements in the routine? You likely identified watching a video of the music coming from the truck and the windows moving in the building nearby, and capturing noticings and wonderings. Additionally, students record their noticings and wonderings of the speaker setup. For our attempt to make sense of the phenomena, you probably identified when students developed initial models, shared those models with partners, and then developed a consensus model. Students identified related phenomena when they brainstormed other times that sound caused something to move or shake. Other times they saw sounds being made or heard sound traveling over distances. Finally, students developed questions and next steps when they brainstorm and revise questions, collectively build a driving question board, and then think of what data they need to answer their questions and what investigations they could conduct to gather that data. Take a minute to think about how the anchoring phenomena routine supported the lessons in being phenomena-based, coherent for students, driven by evidence, collaborative, and equitable. A few things you may have noticed. Having a phenomena that's appropriately complex in the launch of the unit sets the stage for learning that is driven by trying to make sense of phenomena. Instead of learning about a topic, students are trying to answer a question and understand how something in their world works. It is phenomena-based. By allowing students to think to themselves, then work with partners or small groups, and finally share as a class, students have time to have their own ideas, but also share with others and learn from others. Learning is a social act, so the collaborative design supports student learning. These are just a couple of examples of how the anchoring phenomena routine reflects these 5 elements. Now we're going to move into the second lesson of the unit and focus on the investigation routine. To start the second lesson, the teacher can say, in the last class, we had a bunch of interesting questions we wanted to answer about the sound source or the speaker. We noticed that the speaker was moving, but we have some questions about what exactly is happening with the speaker, the sound maker, and with sound makers in general. How can all those different sounds be made? What were some of the ideas for investigations we had around the sound source? The teacher is guided to emphasize ideas such as looking closer at instruments and other things that make sound. At this point, the teacher can ask students to discuss the ideas on the slide and then share out a few ideas. Now that students have shared some ideas, the lesson is designed for them to make in-person, hands-on observations of multiple different sound sources, things like tuning forks, drums, and other instruments. As students move around the classroom observing the different sound sources, these questions are posted to guide their observations and reflections. This is followed by a whole class share out with a focus on the patterns across sound sources and observations. This share out is likely to raise some issues about the students' abilities to see some of what is happening and therefore provide a chance to identify the need to slow the objects down and see what is really happening at a different scale. Students will watch a video of a drum, guitar, and speaker so they could add 3 rows to their table to record their observations. We will watch the speaker and drum videos. Record your observations as you watch. Be as detailed and accurate as you can. Let's watch that again with sound. We will now watch the video of the drum. This video does not have any sound. Students would also watch a guitar, and there is even an additional video of the tuning fork if more videos would be supportive. Students can be given opportunities to share their observations and are likely to have responses such as, sometimes the speaker moved a lot, sometimes not as much. It would get started moving by a drum sound and then keep shaking for a bit afterward. The speaker looked like it rippled like a wave when it moved. About the drum, they might say, it looked like it rippled, or when the stick hit it, it sort of spread out. About the guitar, students might offer that the strings move back and forth, but not always in sync, that thicker strings moved further than skinny strings, and that skinny strings move faster. Once students have collected data, they will have the opportunity to analyze it and try to identify patterns in the objects. After students have had some time to individually analyze their data, they then share with partners. And then they will work with the class to talk about the patterns they noticed and identify how different parts of instruments moved and changed as they were making sounds. This will lead the class to look more closely at what's really happening as an object vibrates and makes sound. Some ideas that are expected to surface are that as objects are struck or plucked or turned on with some sort of force is applied, the object starts to change shape and bend or deform. In all cases, the object didn't directly return to its original shape. It overshot its starting position and changed shape in the other direction. The object repeatedly changed shape back and forth around the starting shape or position. These observations in this conversation will be summarized by saying that all of this changing is what the object is doing when we say that we see objects or feel objects vibrating. When scientists say that something is vibrating, they mean it's moving back and forth repeatedly. Students will use the handout, How Do Instruments Move When Making Sounds, you can see on this slide, to create two models. The first model will be constructed together as a class, and the second can be an individual formative assessment. Let's go through the co-constructed model together. We will use this table to show how one object, in our case the drum, is moving while it's vibrating. This model could be labeled, How do instruments move when they make sound? And we can use the observations that we've been making of instruments that just came out in our building understanding discussion to guide our work. So in the first of the 5 boxes, we can draw and label what happened before we hit the instrument. It's important to note that students would be determining what to put in each box or working together with the teacher. So a question could be asked, like, what did we notice in our observations before we hit the instrument? And the drum wasn't doing anything. It looked like a regular drum with the drum skin flat and the sides in place. And then next we could ask, what happens as it's being hit? So I'm going to walk through the model, but students would be providing feedback. It wouldn't just be the teacher creating this model. When we hit the drum, the drum will change shape or deform. Again, this is connected to the conversation we just had. We're just representing now with a drawing instead of through our discussion. So once we remove that drumstick, we will see that the drum skin is no longer face or pushed down, but rather, and it doesn't even return back to its original place, it goes back up. So we could note that original location on all of these so that we can see the relative position when it deforms below that starting position and above that starting position. And this pattern will continue. So even after it goes kind of above starting position, now it'll go below again. And above again. And back and forth. The class should also work together to know where there are forces being applied, where energy is being transferred, and how this is changing over time. And the final part of the model is what happens after a while. The drum will stop moving and the sound will stop, leaving you with this final model. And the process of the drum skin going back and forth is what we call vibration, what we mean when we say vibration.
Now that we've co-constructed the model, students can be asked to construct a similar model, but using a different instrument they saw, so maybe a guitar. These models can be collected and used as formative assessment. But before that, students can compare their models with a partner and provide feedback to one another using these prompts as support. As students are wrapping up this lesson, they can capture their thinking in their science notebooks by using a progress tracker. A progress tracker is a place where students can set aside, or that students can set aside in their notebooks and come back to throughout a lesson and across lessons and record what they figured out, what they've made progress on. So at this point, the teacher can ask students to help summarize in words what they think is happening in all of the instruments when they make sounds. Students should be able to describe the big idea of the models they created. Finally, students are asked to consider whether all objects, not just instruments, vibrate when they make sounds and record their ideas. Again, students share their ideas with partners and then with the class. The goal of this class discussion is to surface uncertainties about whether all objects, even something solid like a table, are bending back and forth or if they're vibrating when they make sounds. This motivates the class to want to investigate this idea. As noted when we started walking through lesson 2, this lesson consists of an investigation routine. An investigation routine is comprised of 3 parts: creating a plan of action, doing the work with the practices, and sense making or determining what was figured out. Recall lesson 2. What did each of these elements look like in the context of that lesson? Through a guided discussion, students recognized that they needed to make observations of instruments, including instruments making sounds in slow motion. In other words, they collectively created a plan of action. Then students make, record, and analyze these observations. They turn their observations into models by showing each step of how the shape of the drum changed and adding what caused those changes. Students are doing work with multiple scientific practices. While practices can be found in the anchoring phenomena routine and other routines, the investigation routine is when students really get a chance to use the practices to develop an understanding of the disciplinary core ideas and cross-cutting concepts. Finally, the class captures what they have figured out in their progress tracker. Take a minute to think about how the investigation routine supported the lesson in being phenomena-based, coherent for students, driven by evidence, collaborative, and equitable. Investigations are often include phenomena that are related to but different from the anchoring phenomenon. These phenomena ask students to investigate a particular idea and make progress on being able to explain the anchoring phenomenon. As we know, students are investigating in some way and using the scientific practices in the investigation routine. This supports the lesson in being driven by evidence. Students consistently need to think of what question they are trying to answer, what data they need to answer that question, and how to get the data. Then students use their data as evidence to develop models and explanations, support arguments. The order of the investigation routine ensures that the learning is driven by evidence as opposed to having evidence only collected and used to confirm ideas. For our third routine, we're going to look at the navigation routine. Given that students are using different phenomena, anchor and investigations, as we just discussed, moving from one lesson to another in a way that students understand the connection can require thoughtful navigation. The navigation routine also has 3 elements: looking back to figure out how we got where we are, taking stock of where we are now, and looking forward to where we are going. Open-sided lessons are typically designed with students doing as much of this thinking as possible, instead of the teacher providing a recap or telling students where they're going. it is common in an open-sided lesson to look back at the beginning of the lesson, to take stock during a lesson, especially in a longer lesson that lasts multiple class meetings, and to look forward at the end of a lesson. Try to recall the navigation in lesson 2. To start the lesson, the teacher said, in the last class, we had a bunch of interesting questions that we wanted to answer about the sound source or the speaker. We noticed that the speaker was moving, but we have some questions about what exactly is happening with the speaker and with sound makers in general. How can all those different sounds be made? What were some of the ideas for investigations we had around the sound sources? The teacher poses these last questions for the students to do the thinking, what they'll be doing next. But they're also answering the question, how did we get here, in such a way that the observations that they'll make in lesson 2 connect to the first lesson and the ideas that they had then. We ended lesson 2 with the question, do all objects vibrate when they make sound? And our ideas which lay the groundwork for where we are going next. This lesson was not particularly long, so we did not have a moment of taking stock of where we were during the lesson. Let's take a look at the first page of the unit storyline for the sound waves unit. The storyline document that you can see on this slide, and you have a copy of, includes the lesson question and identification of the type of routine that can be found within the lesson. You can see an indication that the first lesson was an anchoring phenomena lesson, and the second was an investigation. The storyline document also includes the anchoring or investigative phenomenon or problem, what students do and figure out, and how it's represented. Between each lesson, there is a description of the navigation to move from one lesson to another. This document is helpful to understand the overall flow or story of the unit before digging into the details of each unit. Take a minute to think about how the navigation routine supported the lesson in being phenomena-based, coherent for students, driven by evidence, collaborative, and equitable. The primary goal of the navigation routine is to ensure that students move from one lesson to another in a way that they understand the connection between them. For this reason, we will focus on how the navigation routine supports the lessons and the unit as a whole to be coherent for students. It's easy to lose track of the larger storyline from lesson to lesson, but when students have the opportunity to look back at how they got to where they are, and also to look forward, the students understand how what they are doing currently connects to the bigger picture. When these connections are understood, each activity has purpose. The navigation routine can also provide an opportunity for students to reflect on their learning over time. For example, the progress tracker can be used as a navigation tool that supports the coherence of the unit. But students can also see how much progress they have made over the unit. The teacher can start the next lesson by asking, what did we discover last time we were together about musical instruments and speakers making sounds? After students have a chance to refresh their memories about the instruments, then the teacher can say, but then we started thinking about the things that aren't designed to make sound. Remind us of some of those examples. This slide then allows students to start to think about and share their ideas of whether these objects that aren't instruments, but that still make sound, would vibrate like the instruments. Students are expected to have different ideas, with some thinking that everything makes sounds will vibrate, while other students are likely to say that still and hard things like a table or a floor cannot be springy enough to move like the instruments, that they don't vibrate. Let's take a look at something that makes a sound that's not designed to make a sound. Did we hear a sound? Did we see any vibration? It seems like we need to gather some evidence about what's really going on here, but we can't see it. Sometimes when we can't observe things like distance or speed, we can change the scale to make them more visible. When we looked at the slow motion instruments, videos of instruments, we had changed the scale of the speed so that we could really see what was going on. At this point, the teacher can say, I was thinking about what we could do to zoom in or magnify on any vibrations that might be happening on the table. I remember trying to use a laser pointer during a presentation one time. It was so hard for me to hold the dot still when it was up on the screen. I think I was nervous, and the laser was magnifying the shakiness of my hand. So I have a laser pointer we can use. How can we design an investigation that would help us see if the table really does vibrate when it makes sounds? At this point, the teacher can work with the class to identify the question they're trying to answer, such as, does a solid, stiff, or hard, or not intended for noise-making object move when it makes sounds? Then they can talk through and set up an investigation using the materials the teacher has, including the laser pointer. The class will eventually create a contraption like this. So here we see the laser pointer that the teacher mentioned changed the scale of their shaking hands. We have that laser pointer mounted and turned on and pointed toward the table that we want to make observations about. On the table, we happen to have a mirror so that the laser pointer doesn't stop there and instead reflects over to, in this case, an easel with a piece of paper on it. So now we'll be able to see or change the scale of what's happening at the table. At this point, students can make a sound on the table again. They could drop a rock like we just saw, or they could hit the table, and then they'll be able to see what happens to the point of light. If it moves up and down, like a vibration, we just saw with the instruments, or if it stays still, if it doesn't vibrate. We can also change the size of the sound and see how that may or may not change the point of light in its changes. What happens with quieter sounds, what happens with louder sounds. While we only looked at 2 slides of lesson 3, we already have seen evidence of the problematizing routine. The purpose of the problematizing routine is to reveal a potential problem with the current model or explanation of the anchoring phenomenon in order to motivate students to extend or revise their models. Similar to other routines, the problematizing routine has 3 elements: foregrounding a new question or phenomenon designed to elicit competing ideas that students can share and support. Since there's disagreement, students need to find a way to resolve the question at hand. How did we see these 3 elements in the start of lesson 3? The new question here is whether any object that makes sounds vibrates, with the phenomena of a rock dropping used to illustrate the question. Some students will think that everything that makes sounds will vibrate. Others will likely say that things that are still and hard, like a table or a floor, cannot be springy enough to move like the instruments. Students need to determine a way to figure out or resolve the problem, in this case, creating the contraption to help scale up their observations. Take a minute to think about how the problematizing routine supported the lesson in being phenomena-based, coherent for students, driven by evidence, collaborative, and equitable. Again, we see that it's trying to explain and make sense of phenomena that's driving the learning here. The phenomenon is different from the anchor or even the investigative phenomena that we saw in the previous lesson. The different phenomena serve different roles. The anchoring phenomenon is complex enough to drive the whole unit. The phenomenon in the problematizing routine is carefully selected to elicit differing ideas that can be argued about and resolved. The process of engaging an argument and determining a resolution requires that the students collaborate, that they share ideas and listen to the ideas of others. Out of this collaboration, students can determine a way to collect evidence that helps them make sense of the phenomena and drives their learning and sense-making. Take a minute to read the unit storyline to find out what else students do and figure out in Lesson 3. Students figure out not only that objects vibrate when making sounds, but that they vibrate more when making louder sounds. But then the question of what it means to vibrate more is raised, which launches students into Lessons 4 and 5. Take a minute to read the unit storyline for Lessons 4 and 5. Students use a motion detector to determine that, in the case of louder sounds, more vibration means that the object moves up and down more. The wave has a higher amplitude. Then students determine that when objects vibrate faster or more frequently, they have a higher pitch sound. Students use mathematical representations of position versus time to make sense of this. This brings students to Lesson 6, which is considered a putting pieces together lesson. Before we look more closely at Lesson 6, let's explore what a putting pieces together routine is. In a putting pieces together routine, students take the ideas they have developed across multiple lessons and figure out how these ideas can be connected to account for the phenomenon the class is working on. The put the pieces together routine serves to help students take stock of their learning and engage with the class to develop a consensus representation, explanation, or model to account for the target phenomenon. This routine typically signifies the end of a group of lessons or a lesson set that helps students make progress on explaining the anchoring phenomenon. Students can return to the driving question board, identify what they figured out and what they still need to figure out, which moves the class into the next lesson. Optionally, students can apply their current understanding, the pieces they've put together, to explain a different phenomena. We're going to use the Lesson 6 materials to identify these elements. Before we do that, let me orient you to the lesson level materials. The first page of the lesson states what students will do and figure out and situates the lesson between the previous and following lessons. The next page provides a learning plan snapshot. This provides a high-level timing of each activity within the lesson. There are also material lists and preparation notes in this section that you will not need right now for finding the elements of the putting pieces together routine. Finally, there's a more detailed learning plan that includes descriptions of each activity with example teacher questions, possible student responses, notes about equity, description of the purpose of the activity, or other things depending on the activity. Now that you're more oriented to the layout of the lesson, take a minute to read through the lesson and identify these elements of the putting pieces together routine. Students take stock of what they know by looking back at their progress trackers and summarizing, by revisiting their exit tickets, and by using the connecting graphical representations to the sounds made document. They then revise their consensus models. There are open-sided units in which students also create a gotta have it checklist at this point. This is a list of all the things a model or explanation of this phenomenon or related phenomena should have. Such a list can then be used by students individually or collectively as they create new or revised models or explanations. Students return to the driving question board and then take an assessment in which they apply the understanding they have developed so far to a similar but different phenomenon of a heart. Take a minute to think about how the putting pieces together routine supported the lesson in being phenomena-based, coherent for students, driven by evidence, collaborative, and equitable. By coming back to the consensus model and revising it as a class, students can see how the learning that they've done across lessons has helped them make progress on the anchoring phenomena and support a sense of coherence. The same is true for revisiting the driving question board. It provides an anchor for the students to continuously come back to, creating a sense of coherence across the learning experiences. The driving question board and revisiting of the board also supports the equity of the learning experience. Every student contributes to the board at the beginning of the unit, as well as when the board is revisited and the class checks in on what questions have been answered in an attempt to ensure that as many questions are answered as possible. This sends the message that all students' questions are a contribution. And finally, we're going to take a minute to think about the final phase of the Louisiana instructional model, communicating scientific reasoning. One of the ways that students do this is through the assessment we just saw at the end of lesson 6. Take a minute to review the assessment and identify the ways in which students communicate their scientific reasoning. Students have the chance to share their understanding through writing and modeling. One of the things students are asked to do is make a claim about which graph matches a given scenario and support their claim with evidence, which requires them to use reasoning. While this particular opportunity to communicate scientific reasoning is a formal assessment that students do individually in the middle of the unit, students are communicating their scientific reasoning throughout the unit in a variety of ways. Anything from writing an exit ticket, to creating an initial model, to turning and talking with a peer can be an opportunity for students to communicate their scientific reasoning. Take a minute to think about how the communicating scientific reasoning supported the lesson 6, and being phenomena-based, coherent for students, driven by evidence, collaborative, and equitable. Using the assessment as the example, the opportunity to communicate scientific reasoning was phenomena-based. This is important for multiple reasons. If lessons and units are phenomena-based, it only makes sense that assessments are as well. Additionally, if we really want to give students a chance to communicate their scientific reasoning, it will be easier for them to do that in the process of explaining a scientific phenomenon. On a similar note, in order to communicate scientific reasoning, students will need to understand and use evidence. Finally, the assessment had multiple ways for students to communicate through writing and developing models. Providing multiple opportunities and multiple modalities through which students can communicate their reasoning allows more students to demonstrate what they know and can do, and in this way is more equitable than a single mode or opportunity. The reflections that I have shared have been focused on the ways in which routines can support key elements. For example, the design of the lesson can support equity and collaboration by asking students to share their ideas, sometimes with partners, sometimes with the whole class. While these experiences are designed into the lessons, they cannot create the class environment that makes students feel safe sharing. In this way, our reflections could have been about how to implement the lessons in a way that supports equity. It is important to consider both the lessons as designed, as well as the implementation in the specific context of a unique classroom. Now that we have more familiarity with the Louisiana instructional model, we will shift our focus to planning for instruction. Please find the Planning Guide for Science Instruction. This tool is designed to support teachers as they collaboratively prepare to deliver high-quality instruction, and as they collaboratively analyze student work. The planning guide is organized into 4 steps: unit unpacking, unit launch deep dive, lesson set annotation, and student work analysis. Let's start with looking at step 1, unit unpacking. The goal of this step is to ensure that we have an overview of the unit before we dig into the details of each lesson. Take a minute and read through step 1. This step includes understanding the phenomenon students will be able to explain at the end of the unit, the 3 dimensions the students will learn and use to explain the phenomenon, and the overall story of how students move through the unit. In open-sided units, there are often resources in the instructional materials to help answer these questions in step 1 and get an overview of the unit. For example, the unit storyline that provides an overview of how students move through the unit in a coherent way to incrementally build understanding and eventually explain the phenomenon. One of the questions in step 1 asks you to consider how students will build on previously learned content. There will likely be some of this information in the curriculum documents. An additional resource that can be useful in answering this question is the disciplinary core ideas learning progression. This document shows how each of the core ideas, in this case waves and their applications, change in sophistication over the grade bands. Using these progressions allows you to understand what students have previously learned in school and what they will learn later. This helps better define what is required of students at your given grade band. Step 2 of the planning guide is a more detailed look at the launch of the unit. Take a minute to read through this page. You likely notice that step 2 is asking questions about the 4 elements of the anchoring phenomenon routine. For example, if we were using this document to unpack the sound waves unit we just walked through, the explore phenomena activities would be watching the videos of music coming from the truck and the windows moving, observing the speaker setup, and recording noticings and wonderings. The questions encourage teachers to not only identify the elements of the routine, but to think deeply about the elements and the implementation of the launch. For example, under the Identify Related Phenomena element, we will brainstorm the phenomena that students may identify based on what is relevant to them and consider how students will connect to the examples. The third step of the unpacking guide is lesson set annotation. You may remember that in the sound waves unit, lessons 1 through 6 represented a lesson set, and that within OpenSciEd, the end of a lesson set often includes putting pieces together routine. Lesson sets are subsets of lessons within the unit that hang together based on students figuring something out about the anchoring phenomenon. Take a few minutes to read through step 3. Lesson sets will include investigations in which students get opportunities for rich, 3-dimensional learning. You may have noticed other connections to routines we just explored as we walked through the instructional model. The most obvious is where the planning guide instructs users to identify the instructional routines they will use. A less obvious example is that competing ideas can be found in problematizing routines. The final step of the planning guide is to analyze student work. Take a few minutes to read through this step. The protocol for analyzing student work can be found on this slide. As noted, the criteria should use performance expectations in the task. In curriculum such as OpenSciEd, there are often lesson-level performance expectations that are a smaller grain size than the standards, and therefore more appropriate for lessons. Tasks also often identify the 3 dimensions that the task should be eliciting evidence of. If this information exists, it may be sufficient criteria. It is also possible that you will need to further narrow the given information to have usable criteria. For example, it may be clear that students are supposed to develop a model, but you may decide to specify that models should include more or less dense air, as seen in this student model. or in the model that we created together, a starting position of the drum. Criteria may have also been created by students as they developed a gotta have it checklist. Regardless of how criteria are set, trying to ensure that everyone analyzing student work understands the criteria during the first step is very important, as this is how exemplars will be determined in the second step and used for the analysis in the third step. If the group has trouble identifying exemplars and analyzing work, it may be worth considering revisiting the criteria to make sure the group is clear and modifies the criteria as needed. The goal of this step is to better understand what students know and can do and use that to inform further instruction. Thank you for joining this recorded webinar to learn more about the Louisiana Instructional Model and Planning Guide. Use the questions on the slide to guide your reflection for the session.